Reaction mechanisms explain the series of steps by which a reactant changes into a product or products. Reaction mechanisms can have a single step or multiple steps involved. What they all have in common, though, is that the slowest step within a reaction mechanism is ultimately what determines the rate law. After all, a reaction can only go as fast as the slowest step. Here we see a reaction mechanism for nitrogen dioxide reacting with carbon monoxide to exchange an oxygen between the two molecules. This two-step mechanism involves step 1 being a slow step, or the slowest step of the reaction, and step 2 simply having a faster rate than step 1. So what can we get from this mechanism? Well, we know the rate law is got to be dependent upon the slowest step. Therefore, the nitrogen dioxide we expect to be in the rate law. Because the step that's the slowest has two NO2s as reactants, that means we write the rate law as based off of the reactants. The rate is equal to the rate constant K times nitrogen dioxide squared. This is unlike an overall balanced equation where we can't do this. We can only use steps in a rate law to determine a overall rate law for it. That is, you can't use an overall balanced equation to determine a rate law, but you can use the slowest step in a mechanism to determine the rate law. So, when we look at this mechanism, we'll note that even though carbon monoxide is a reactant in the overall reaction, we find that nitrogen dioxide is the only molecule that controls the rate of this reaction. It's also worth noting that nitrogen trioxide is created in the first step of the reaction as a product, but we see in step 2 nitrogen trioxide is a reactant and it doesn't appear in the overall reaction. Such molecules which are created and destroyed during the course of the reaction are known as intermediates. However, not every reaction mechanism has the first step as the slowest step. Yet the slowest step is always what determines the rate law. All other steps are assumed to occur faster than the slowest step, and therefore the reaction is allowed to come to equilibrium in that step. That is, the reaction achieves a point where the forward reaction and the reverse reaction are occurring at the same rate. This isn't true for the slow step, but for all the other steps we can assume that this is. When we write the rate law for a slow step, we always base it off the reactants. And so we would predict the rate law for this reaction would be the rate equals the rate constant of step 2 times nitrogen monoxide dibromide times nitrogen monoxide. The problem with this, though, is that if we go back and we look at the actual mechanism, we don't see NOBr2 in the overall reaction. This creates a problem for us because we don't know what the nitrogen dibromide concentration is, and it is not something that we could easily measure, as it's constantly being created and destroyed during the course of this reaction. So using intermediate molecules in a rate law is somewhat problematic. But we can get around this because we know from the first step that nitrogen monoxide and bromine come together to form this molecule, and they do so relatively fast. We also know that this step achieves equilibrium, therefore we can say that the rate of the forward reaction and the rate of the reverse reaction are equal to each other. So we can use the reactants in that first equation to write the rate of the forward direction, that is K1 times NO times Br2, must be equal to the rate constant of the reverse reaction, that is K minus 1, times NOBr2. We can then solve for the concentration of NOBr2 in terms of original reactants, nitrogen monoxide and bromine, and then substitute it in to our rate law from the second step, giving us that the rate of the reaction is equal to the rate constant K, nitrogen monoxide squared, times bromide.